Good morning everyone, I'm Jun Chris Vidad, and in this video, we're gonna talk about the convolution of two different functions. We actually have three different goals, and the first goal is to simply define what is the convolution of two functions is, and then I want to investigate what several common properties of convolution are going to be, and then finally, and this is where the goal is here, is how can I use the new operation and functions called the convolution to help me solve problems of inverse Laplace transforms. Okay, so how should we define it? First things I want to think about is that if you have a function of f at a function of g, there's a couple different ways you could combine the two functions. For example, you could take f and then you could add to it the function g, or you could take the function f and you could multiply it to the function g. What I'm going to give here is a third way that I could combine functions. It's called the convolution. We denote it with a star, so this notation read the convolution of the function f of t with the function g of t. This star that I have here is not the same thing as multiplication. This is a new operation, something new that takes two different functions and combines them to your third function. The way this is defined might seem at first kind of weird. It's defined to this particular integral. It's an interval from 0 up to t of f of tau, being a dummy variable of integrations times g of t minus tau, and then all integrating respect to tau. If I look at this right hand side well, all of this together is just some function of t. The tau's are integrated out and there is a t first inside of the g. But also, secondly, in the limit of integration, so from 0 up to t, there's two different places that t remain, and nevertheless, it's a function of t as long as I presume that my f and my g are actually able to be integrated. Then I have this nice object called the convolution. To consider the particular object, but I want to study his properties and see how to be so how it's going to be. So useful to us nevertheless, and indeed anytime I come up with a new operation. For example, maybe in a linear algebra, you figure out how to do matrix multiplication. Usually, that's what kind of properties does the new operation have. This one has several. The first is that it plays nicely when you interchange the order. It has a cognitivity property, but the convolution of f and g is the same thing as a convolution of g and f. We're gonna prove this property in a movement, but let me state the second one, which is going to be a associativity property, the convolution of f with the convolution of g and h. The same thing as the convolution of f and g, and then you take the convolution of that with itself, that is a subjectivity property. And then finally, we also have a distributivity property, which is that convolutions and normal addition of functions also play together. So if you take the convolution, as they say, over the addition of functions, and you get the convolution of f with g, and you just add the convolution of f with h. So the first one is the conductivity one. I'm gonna begin with the convolution of f of g and add either kind of alternate row. Basically, what to do is interchange the role of f and g here, and I'm going that well just with the substitution. So I'm going to define a new variable u, which is the difference, this t minus tau, and I'm going to take the change of variables and plug it. So if I do that, it gives me the following thing. The g of t minus tau, it turns with g of u. The f of tau turns it an f of t minus u. The d tau turns into a negative du. That's why there's this negative sign at the front. And finally, limits of integration. Change if you plug in tau equal to 0. You're gonna get u equal t. And if you plug in tau equal to you're gonna get u equal to 0. So that's why with these limits of integrations going from t on the both of going t to the bottom to 0 on the top, it's interchange. Okay, so what can I do? Well, I see there's a negative on the front. And so if I can use a negative to interchange lowest of integration, so doing that is just gonna give me the to go from 0 up to t of this expression. And the second thing to do is I'm going to alternate the order, the f and g, just change which comes first, which comes second, and the point is that with those rearrangement, the interval that they have is not exactly the same, the convolution. But with f and g interchange, that is this just a convolution g and f, g with f, as opposed the convolution of f with g. And that's all my report about convolution. Have a nice day and thank you for watching.